Engineering workflows generate massive amount of spatial data, coordinates, dimensions, performance metrics, and load values. But trying to interpret that 3D reality through a 2D spreadsheet creates a bottleneck. You are staring at rows of numbers when you actually need to see physical space. Instead of reading those rows, you can pass them through a script that instantly compiles the raw data into a fully realized spatial environment. The numbers becomes geometry, layout, and structure in seconds. Many engineers overlook Blender because they view it as a subjective tool for artists and animators. The assumption is that it requires manual drafting and handmade graphics. Beneath the graphical user interface, the software functions as a data visualization and parametric design engine. Blender exposes its entire internal architecture through a Python API. By writing scripts, you can entirely bypass the manual process of 3D modeling. A 3D environment is a programmable software system. You define the logic and the scene is generated from those rules. The formula represents the automated workflow. We take structured input data, process it through Python logic, generate a Blender scene automatically, and output clear visual insight. Raw parameters translate directly into automated designs and digital twins. Shifting from manual object creation to algorithmic system generation is the foundation of the modern engineering pipeline. To generate these systems, we have to understand the architectural foundation of the software. Everything in Blender relies on a specific Python API structure to function. This diagram shows the architecture's three pillars. First, bpy.data is the database storing all geometries and materials. Next, bpy.context is the state tracker reading current selections. Finally, bpy.ops is the command layer executing the same actions a human user would trigger. We can apply this architecture to a practical baseline. Suppose an engineer has a simple spreadsheet containing a list of machine performance values from a factory floor. Here, a script reads an array behind an empty 3D workspace. A loop iterates through that data, spanning a cube for each value. Math scales their vertical height proportionally. Then conditional logic assigns color, green for normal, yellow for warning, and red for a critically low. Throughout this entire sequence, the user performs no manual 3D modeling. Raw numbers have been algorithmically compiled into a spatial, immediately understandable 3D dashboard. We can scale the same baseline logic to generate complex structural geometry, like a truss bridge. We define structural rules upfront using a parameter block, establishing variables for span, panels, deck elevation, and height. Using these, the script calculates spatial coordinates for the bridge nodes. Looping logic then connects these coordinates, generating lower chords, upper chords, and vertical members automatically. The core advantage of this specific workflow is the ability to execute the structural iterations without rebuilding the model. Changing a single variable, like increasing the structural panels from 8 to 14, forces the system to instantly recalculate the nodes and redraw the geometry. This parameter-driven method aligns with an engineering mindset of constant iteration, shifting the workload from manual drafting to encoding the mathematical rules defining the structure. We can also apply this parametric logic beyond single structures, moving into site planning and layout automation. Consider a scenario where we arrange a utility scale solar array. We start by inputting parameter for rows, columns, spacing between units and panel tilt angle. This diagram shows a top-down view of our site. A nested loop logic allows the system to evaluate every coordinate on the grid, placing a support post and a tilted panel at each intersection. Generating layouts automatically allows rapid scenario testing based on site constraints. Engineers test energy capture by adjusting tilt parameters, watching the geometry update to reflect new sun angles. Adjusting row spacing lets the team evaluate maintenance assess and measure new land usage footprints. Updating a massive site layout by hand in traditional drafting software is slow and prone to placement errors. Here, the math handles the exact precision. This automated workflow creates an operational loop for the engineer, change the parameter, regenerate the layout, and compare the physical outcomes. These powerful algorithmic scripts form the bedrock for large-scale industrial digital twins. The next step is the data integration layer. The hard-coded variables in these scripts can be replaced by dynamic data sources. External data like live sensor networks, GIS constraints, or CSV files can be fed into the script to drive the geometry in real time. This diagram illustrates the modern engineering pipeline. It begins with establishing the rules through script logic and feeding the system project data. The third phase introduces AI. Artificial intelligence works on top of the script to automate the input parameters. AI generates thousands of variants in seconds, finding high efficiency configurations. Fourth, the 3D software acts as the visualization engine, rendering outputs spatially. Finally, an engineer reviews the visual data, applying their judgment to validate the safety and design practicality. This powerful pipeline seamlessly integrates the rapid speed of automated iteration with the critical oversight of an experienced engineer. As this text illustrates, code defines the rules, AI expands the possibilities, engineers make the decisions. Utilizing the API allows 3D software to function as a programmable ecosystem for building and testing engineering systems.